Okay, in this video, we're going to talk about section 3.2 dealing with measures of variation. So here we're going to develop the ability to measure variation in a set of sample data by finding values of the range, variance, and standard deviation. Also, we'll develop the ability to interpret values of the standard deviation by applying the range rule of thumb to determine whether a particular value is significantly low or significantly high. Okay, so the first thing we'll talk about is the measures of variation and its basic concepts. So here the measures of variation communicate the spread or dispersion of data. In our last video, we talked about the measure of center, how they are centered, how those data values are centered. This time, we're dealing with variation, okay? The spread or the dispersion of data. And there are going to be three important measures of variation that we will talk about. One of them is the range. The second is the standard deviation. And the third is the variance. So let's talk about the range of a set of data. So that's the first thing we'll look at here. The range of a set of data values is the difference between the maximum data value and the minimum data value. Okay. Now this one is kind of the easiest one to do because the range is just simply taking the maximum data value minus the minimum data value. That number would be the range of that data set. Now, because the range uses only maximum and minimum data values, it's very sensitive to extreme values, and it is not as useful as other measures of variation that use every data value, like in this example here. Let's say I want to find the range of the Verizon data speeds in megabytes per second. And these are the data speeds: 38.5, 55.6, 22.4, 14.1, and 23.1. So to find the range, we just take the maximum data value. In this case, that's 55.6 minus the minimum data value. That would be 14.1. So 55.6 minus 14.1 will be equal to 41.50 megabytes per second. Okay. And notice that this is carried out to one more decimal place than the original data set. So this brings up the round off rule. When rounding a measure of variation, you're going to carry one more decimal place than is present in the original data set. So in this case right here, it was to one decimal place, and that means that the range has to be to two decimal places. If my data set was just whole numbers, then the range would be carried out to only one decimal place. Okay. All right, next we'll talk about the standard deviation of a sample. By definition, the standard deviation of a set of sample values, which is denoted by lowercase s, is a measure of how much the data values deviate away from the mean. Okay. And to find the standard deviation, we do have a couple of formulas. In this case here, this is how we would calculate the standard deviation. It's the formula here. It'll be the square root of the summation of x minus x bar, and that quantity is squared, divided by n minus 1. The way you'll have to find that standard deviation is kind of tedious. You have to find out what the mean is first. And then you have to take each individual data value, subtract that data value minus the mean to get what they call the deviation. And then you have to take the square of each of those deviations. That's where that square comes from. And then take the sum of those deviations. And then that's going to be divided by n minus 1. And n is the sample size. The one we're going to use is formula 3-5. We call that the shortcut formula for a sample standard deviation, because all you're going to be dealing with in this case is just x and x squared. Okay. So standard deviation for that sample, that'd be s is equal to the square root of n, that's the sample size, multiplied by the sum of your x squares minus the sum of all your x values, and then that's going to be squared. So it's the square of the sum of the x's subtracted from this product here. That difference will be divided by n times n minus 1. Now, let's talk about some of the important properties of the standard deviation. All right, the standard deviation is a measure of how much data values deviate away from the mean. And then number 2 is the value of the standard deviation, lowercase s, is usually positive. It is 0 only when all the data values are the same number. It is never negative. So you're never going to get a standard deviation that's negative. Also, larger values of S indicate greater amounts of variation. Okay. And then the value of the standard deviation can increase dramatically with the inclusion of one or more outliers. Okay, outliers, again, those are your data values that are very far away from all the others. And then the units of the standard deviation, which is S, such as minutes, feet, pounds, and so on, are the same as the units of the original data values. And then the sample standard deviation is a bias estimator of the population standard deviation, which is this Greek letter sigma, lowercase sigma, I should say. Okay. All right, now let's compare the variation in simple samples here. We'll talk about that. It is a good practice to compare two sample standard deviations only when the sample means are approximately the same. When comparing variations in samples with very different means, it is better to use the coefficient of variation. Okay. Now we won't talk about the coefficient of variation in this video here. All right, but if we're dealing with the standard deviation of a population, notice we use Greek letter sigma. Okay. And for the mean, we're using a Greek letter mu. And notice that capital letter N is the population size. And we're not using, in this case, n minus 1. And the shortcut formula is also slightly different from the simple standard deviation formula. Okay. All right, next we'll look at variance. Once you find the standard deviation, the variance is going to be very easy. Here the variance is a set of all value. The variance is a set of values of a set of values is a measure of variation equal to the square of the standard deviation. So in other words, when you find this standard deviation, easily you can take the square of that standard deviation to come up with your sample variance. Okay. So when we do some of these examples here, we'll start by finding the standard deviation first. And whatever that standard deviation is, the variance can be easily found by just taking the square of that standard deviation. Okay. Okay. So here the population variance, which is of course sigma squared, that's going to be equal to the square of the population standard deviation, which is lowercase sigma. So here we have a summary of just a notation for standard deviation and variance. So here, lowercase s is a sample standard deviation. Lowercase s squared is a sample variance. Lowercase sigma is a population standard deviation, and lowercase sigma squared is a population variance. Okay. Now, there are important properties of variance. One of them is that the units of the variance are the squares of the units of the original data values. For example, if the original data values are in feet, then your variance will be in feet squared or square feet. The value of the variance can increase dramatically with the inclusion of one or more outliers. And just like the standard deviation, the value of the variance is usually positive. It is zero only when all the data values are the same number. It is never negative. And the sample variance, which is s squared, that's going to be an unbiased estimator of the population variance sigma squared. Okay, lowercase sigma squared. Okay, so those are the formulas for finding the range, the variance, and the standard deviation. So let's apply those formulas to these examples here. Like in example 1. Listed below are the top 10 annual salaries in millions of dollars of TV personalities. Find the range, variance, and standard deviation for the sample data. Given that these are the top 10 salaries, do we know anything about the variation of salaries of TV personalities in general? Okay, so here's our data set here that's given to us. So let's start by finding the range, because that's easiest. So to find the range, it's going to be the maximum data value. I'll just say maximum value minus the minimum value. Okay. So here, the maximum value or the highest data value in this data set is 38. And this does look like it's already in numerical order, so the highest number is 38. The minimum is 11.5. So if I take 38 minus 11.5, you'll get 26.5. So the range of this data set is 26.5. Okay, now let's find the variance. Now the variance is going to take a little bit of time to do because of the number of data values that we have here. And the way we set this up is this. I'm going to do 2 columns. One would be the x, those are my data values that I have here, and x squared would be the square of each data value. Okay, so let's go ahead and list these data values here. It'll be 38, 37, 36, 29, 18, 17, 16, 13, 12.7, and finally 11.5. Okay. Now, here I'm going to put the summation of my x's here. So that means I'm going to add all of these x values that I have here. Okay. So when I add 38 plus 37 plus 36 plus 29 plus 18 plus 17 plus 16 plus 13 plus 12.7 plus 11.5, I will get 228.2. That's the sum of all the x values, 228.2. Okay. Now for the x squared, here I'm going to square each individual data value here. So if I square 38, that means 38 times 38, which will give you 1,444. If I square the 37, 37 times 37 is 1,369. Square the 36, that's 36 times 36, which would be 1,296. 29 squared will be 29 times 29, that's 841. 18 squared, 18 times 18, which will be 324. Square the 17, you'll get 289. 16 squared will be 256. Square the 13, you'll get 169. And square the 12.7, 161.29. And finally, 11.5, you square that, that'd be 132.25. And now, if I take the sum of all of these, I will get the sum of my x squares. And if I add these numbers up together, the sum of all my x squares, I get 6,281.54. Okay. Now, from here, I can find the variance. But first, let's count up how many data values that we have here. Well, in this case, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I get 10 data values here. That's n. That's your sample size. It will be equal to 10. So now for the for the variance. I'm finding the variance first. Once I find the variance, I can easily find the standard deviation. Okay. And the formula for finding the sample variance, well, if I know what the formula for the standard deviation is, which is this right here, I'm using a shortcut formula. Okay. If I square both sides, this will eliminate the radical. So what's underneath that will be what the sample variance will be. And that's, of course, n times the sum of your x squares minus the sum of the x, that sum is squared, divided by n times n minus 1. So all we do there is just substitute in that particular formula. So here s squared will be equal to n, which is 10, times the sum of the x squares. If you look down here, we found the sum of the x squares to be 6,281.54. Minus the sum of the x. The sum of the x is 228.2. And that's going to be squared. All divided by n, which is 10, times n again, that'll be 10 minus 1. Okay. So here s squared is equal to, let's do the numerator and the denominator separately. The numerator is going to be 10 times 6,281.54 minus 228.2. And there's a button on this calculator that says x squared. It's right here. Press that button, you'll get the exponent of 2, because you want 228.2 to be squared. And then that'll be subtracted from 10 times 6,281.54. So the numerator is going to be 10,740.16. Then the denominator is your 10 times 10 minus 1. So I type in the number 10. And 10 minus 1 is in parentheses. So I'm going to use left parentheses here, which is above the number 8. And then type in 10 minus 1. And then close the parentheses. The right parentheses is above number 9 on your graphing calculator. And then hit enter. That bottom number, that denominator is going to be 90. So I got 10,740.16 divided by 90. And that's going to be equal to so here I'm going to get approximately, and we're going to round that variance to, let's say, 2 decimal places. So in this case here, the second number after the decimal point is a 3. To the right of it is 5. This 3 will increase to a 4, so it'll be 119.34. So the variance in this case is 119.34. Now to find the standard deviation, that's just S. And this standard deviation is just a square root of your variance. Here our variance is 119.34. So it's going to be the square root of 119.34. I'm going to do second x squared for the square root. 119.34. To 2 decimal places, this will be approximately 10.92. So the standard deviation of this data set is 10.92. Now, the other part of the question is, given that these are the top 10 salaries, do we know anything about the variations of salaries of TV personalities in general? And the answer for that would be no. And the reason for that is because the sample here is not representative of the entire population. Okay, it's just a sample of 10. So here, sample data is not. We don't know that those data values are a representation of the entire population. Okay. So that's how you find the range, the variance, and the standard deviation of any data set. Okay, here's another example. Let's say listed below. Listed below are the prices in dollars for one night at different hotels in a certain region. Find the range, variance, and standard deviation for the given sample data. Include appropriate units as in the results. And how useful are the measures of variation for someone searching for a room? Okay. All right, so now here's that data set that we have here. Now we want to find the range, which is going to be the easiest easiest one to find. So here the range in this case would be the maximum minus the minimum data value. I just say maximum minus minimum. So here the maximum data value here is 291 minus the minimum, which is in this case 90. So if I do 291 minus 90, I would get 201.0. And this will be in dollars because the prices that are given in that data set are in dollars. So the range will have that unit in dollars. And notice that I carried it out to one more decimal place than it is given in the data set. Here my data set are whole numbers, so that means I need to carry it out to one decimal place. Okay. And now comes the hard part, finding the variance. And again, like I did in that last example, I used the shortcut formula. I'm going to do the same thing here. Say I'm going to list all my data values here in X. So it'll be 191, 104, 114, 189, 243, 291, 126, and 90. Now we're going to find the sum of the x's here, which I've already did here. If you add all of these numbers here together, that sum would be 1,351. And let's count how many data values we have here while we're at it. In this case, there are 8. So n would be equal to 8. That's your sample size. And now the x squared, we just square each individual x value. So if I square 190, and that should be 194. Not sure where I got 191 from. This should be 194. So if I square the 194, that's 194 times itself, it'll be 37,636. And then 104, square that would be 10,816. 114, you square that, it'll be 12,996. And then 189 squared would be 35,721. And then 243 squared would be 59,049. And then 291 squared would be 84,681. 126 squared would be 15,876. And if I square 90, 90 times itself, 8,100. And if I take the sum of these x squares, if I take the sum, add these numbers, these x squares together, I would get 264,875. Okay. So this represents the sum of the x's. This represents the sum of the x squares. So now to find the variance, I'm going to use this formula, s squared equals n times the sum of the x squares minus the sum of the x, and that's squared, divided by n times n minus 1. And then we just substitute in that formula here. So S squared would be equal to N, which is 8, times the sum of the X squares, that's 264,875, minus the sum of the X, that's 1,351, and that 1,351 will be squared. All that's divided by N, which is 8, times N again, that's 8 minus 1 in parentheses. Okay, so now let's simplify the numerator and the denominator. And that will tell us when we divide, let's see, the numerator will be 8 times 264,875, and then minus 1,351, and then hit the X squared button on the far left, and then hit enter. So that numerator will be 293,799. That'd be divided by, the denominator would be 8. Then I'm going to do left parentheses, 8 minus 1, because it will do 8 times 8 minus 1, which would give me 56. So it'd be 293,799 divided by 56. And to one decimal place, this will be 5,246.4. Now, we have to use the appropriate units here. For the variance, it's going to be dollars square, because it is a variance, okay? So it has to be dollars square, and variance is S squared, okay? All right, and now for the standard deviation. That's, of course, S is equal to the square root of S squared, which is the variance. The variance is 5246.4. So if I take the square root of 5246.4, to one decimal place, this will be approximately 72.4. And the standard deviation in this case, since the variance is in dollars square, the standard deviation, if you take the square root of that, it will be in dollars. Okay. So that's how we find the range, variance, and standard deviations, and using their appropriate units. Now, how useful are the measures of variation for someone searching for a room? In this case, it's not going to be useful for you, because you have to take in certain factors of searching for a hotel room, like the price, can you afford it? The location, where is that? The accommodations, are they good or are they bad? Those factors are more important than just the amount of the variation. Okay, so you have to look into other factors of renting a hotel for one night or for many nights. Okay, now example 3. Listed below are the number of hurricanes that occurred in each year in a certain region. The data are listed in order by year. Find the range, variance, and standard deviation for the given sample data. Include appropriate units in the results. What important feature of the data is not revealed by any of the measures of variation? So here's our data set that you see. Now we can find the range first. That is, again, the maximum value minus the minimum value. Your maximum is, in this case, 18, minus the minimum. In this case, is 3. So 18 minus 3 would be 15. And since it's a whole number, the range has to be carried out to one more decimal place. So it'll be 15.0, and we have to use the appropriate unit. Since we're dealing with hurricanes, the range will be 15.0 hurricanes. All right, next we'll find the variance. I'm going to go ahead and count up the number of data values that we have here. We got 2, 4, 6, 8, 10, 12, 14. So you got 14 data values here. Okay. So here, I'm going to write my 2 columns for x and x squared and list all my x values here, which is in this case 16, 7, 6, 5, and 5, then 3, 13, 13, 8, 11, 18, 11 again, 14, and 4. Now, if we add all 14 of these data values that we have here, you should get 134. That's the sum of the x, 134. Now, for the sum of the x squares, we need, for the x squares, we need to square each data value and then get its sum. Okay, so if I square 16, this will be 256. Square the 7, 49. Square the 6, that'd be 36. Square the 5, that's 25, and I got another 5, that's also 25 when I square that. Square the 3, it'll be 9. Square the 13, that'd be 169. And I got another 13, so that's 169 again when I square that. Square the 8, that's 64. Square the 11, 121. Square the 18, 324. Square 11 again, 121. Square the 14, I'll get 196. And square the 4, it'll be 16. So if I take the sum of the x squares, add those numbers together, I will get 1,580. So the sum of the x squares will be 1,580. So now to find s squared, or the variance, which is what the notation is for that, it will be n times the sum of the x squares minus the sum of the x's that will be squared divided by n times n minus 1. So here we just substitute. N in this case is the number of data values that I have, that's 14, times the sum of the x squares, that's 1,580, minus the sum of the x, that's 134, it will be squared, divided by n, which is 14 times n again, that's 14, and then minus 1 in parentheses. Okay, so let's add those numbers up. Let me clear this out. 14 times 1580 minus 134, and that's squared, would be 4,164 in the numerator, divided by 14 times 14 minus 1. That's 182. So if I take 4164, divide that by 182 to one decimal place, this will be approximately 22.9. And the variance is in square units, so it has to be hurricanes square. Okay. So remember, with the variance, your units has to be in. It has to be that unit squared. So in this case, 22.9 hurricanes squared. All right, and then we find the standard deviation. And that's always the square root of your variance, that's square, which we found to be 229. So if I take the square root of 22.9, which is my variance, second x squared for the square root, 22.9, hit enter. This will be approximately, to one decimal place, 4.8. Okay. And it'll be 4.8 hurricanes. Now put the square, because the square root makes it the unit itself. So the standard deviation there is 4.8 hurricanes. Okay, the other part of the question is, what important feature of the data is not revealed by any of the measures of variation? Well, the measures of the variation reveal nothing over a pattern of time. Okay, it just doesn't tell us anything over time. So that's how we find the range, the variance, and the standard deviation of any data set. Okay. Now let's talk about the range rule of thumb for understanding the standard deviation. Now there are going to be three different concepts that will help us understand and interpret values of the standard deviation. One of them is the range rule of thumb. The second is the empirical rule, and the third would be Chebyshev's theorem. First, we'll talk about the range rule of thumb. The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. It is based on the principle that for many data sets, the vast majority, such as 95% of the sample values, lie within two standard deviations of the mean. Okay? Two standard deviations of the mean. We use that to help us determine whether we have, say, significantly low values or significantly high values. Okay, so here's how we interpret a known value of the standard deviation. If the standard deviation of a collection of data is a known value, we can use that to find rough estimates of the significantly high and significantly low sample values as follows. So here is that range rule of thumb. For significantly low values, they're going to be mu, which is just mean, minus 2 times sigma, which is the standard deviation. Mu minus 2 times sigma or lower. And then significantly high values are going to be mu plus. Okay. Need to correct that because that should be plus. Mu plus 2 times the standard deviation or higher. Now, values that are not significant are the ones that are between mu minus 2 times sigma and mu plus 2 times sigma. Keep in mind, mu is the mean and the sigma is your standard deviation. Okay, so here is a kind of an illustration of that. The values that are not significant are going to be between the significantly low value and the significantly high value. The significantly low values are going to be to the left of the low value, and significantly high values are going to be to the right of that significantly high value. Okay. All right. And also we can estimate the value of a standard deviation. To roughly estimate the standard deviation from a collection of known sample data, we can use this. S is going to be approximately equal to the range divided by 4. And here the range, again, that's the maximum data value minus the minimum data value. So you'll take that difference and divide that by 4. You'll get a rough estimate of what the standard deviation is. Okay. All right, here's example 4. A certain group of test subjects had pulse rates with a mean of 77.1 beats per minute and a standard deviation of 12.9 beats per minute. Use the range rule of thumb to identify the limits separating values that are significantly low or significantly high. And then using that, we can answer this question: is a pulse rate of 142.9 beats per minute significantly low or significantly high? All right, so let's look at what we already have. We have a mean of 77.1 beats per minute. So that's mu. And the standard deviation of 12.9 beats per minute. That's going to be our sigma, our standard deviation. Okay. So let's find the value that would put it at significantly low. Okay. That's the value that's going to separate the values, the ones that are significantly low. And of course, significantly low means this. We have to do mu minus 2 times sigma, or the mean minus 2 times standard deviation. Our mean is 77.1 minus 2 times the standard deviation of 12.9. Okay. Now we can do this in the calculator by saying this 77.1 minus 2 times 12.9. So 51.3 is the limit that separates values that would be considered to be significantly low. So 51.3 or lower than that is considered significantly low. Now for significantly high values, or the limit that for significantly high values, this time is going to be mu plus 2 times the standard deviation, or sigma. Again, your mu is 77.1. This time it's going to be plus 2 times the standard deviation of 12.9. Okay. The mean and the standard deviation are the same. The only difference there is this: you just have to change one from a minus to a plus. So in this case, it'll be 77.1 plus 2 times 12.9. So it'd be 102.9. So any value that's 102.9 or greater is significantly high. If you have a value that's in between these two, then that value is not significant. Okay. Now, is a pulse rate of 142.9 beats per minute significantly low or significantly high? So, well, 142.9 is greater than 102.9. Okay. So we can say here that 142.9 beats per minute. Since it's greater than 102.9, it is significantly high. And that's because it's more than 2 standard deviations above the mean. Okay. So that's how we use the range rule of thumb to determine whether a value is significantly high or significantly low. Okay, another way we can do this is, well, the next thing we'll talk about is the empirical rule for a bell-shaped distribution. Sometimes it's called the 68-95-99.7 rule. Okay. Now this concept is helpful in interpreting the value of the standard deviation. And it states that for data sets having a distribution that is approximately bell-shaped. So here these properties apply. One is this: approximately 68% of all the values fall within one standard deviation of the mean. So if you look at this normal curve that we have here, one standard deviation, here's the mean right here in red. One standard deviation below and one standard deviation above. That represents 68% of the data values. And then next, about 95% of all data values fall within 2 standard deviations of the mean. So here, 2 below the mean and 2 above the mean. That represents 95% of all values within 2 standard deviations of the mean. And then finally, 99.7% of all values fall within 3 standard deviations of the mean. So here we're looking at 3 below and 3 above. 3 standard deviations below, 3 standard deviations above. That's 99.7% of your data values within 3 standard deviations of the mean. So here we're going to be using that concept of the empirical rule to help us answer the next question in example 5. And that's this: the blood platelet counts of a group of women have a bell-shaped distribution with a mean of 206.8 and a standard deviation of 65.5. All units are 1,000 cells per microliter. Using the empirical rule, find each approximate percentage below. So here we got 2 parts. What is the approximate percentage of women with platelet counts within 3 standard deviations of the mean, or between 64.3 and 457.3? And then part B, what is the approximate percentage of women with platelet counts between 129.8 and 391.8? Okay. What I'm going to do is draw the normal curve to the best of my ability here. So here's the horizontal axis here. Here's the bell-shaped curve. So the X bar, which is the mean, that's at the center, which is at the highest peak of that normal curve. And then I'm going to draw three tick marks, 3 standard deviations above and 3 standard deviations below. Now, if you recall, this will be X bar plus 1 standard deviation, then X bar plus 2 standard deviations, then X bar plus 3 standard deviations. And those are S's. To the left of the mean will be X bar minus 1 standard deviation, or just X bar minus S. Then next will be X bar minus 2 standard deviations, and then X bar minus 3 standard deviations. Now we know 2 things, that the mean of that is 260.8, and the standard deviation is 65.5. So my mean is at 260.8. That goes here. To get the values that are 1, 2, and 3 standard deviations, I just keep adding the standard deviation of 6.5 each time. So 1 standard deviation above would be 260.8 plus 65.5. That would be 326.3. And then 2 standard deviations, I just add another 65.5 to the 326.3. That would be 391.8. And add another 65.5, that would be 457.3. To the right of that, I just continue to add 65.5. Now to the left of that, I'm going to continue subtracting 65.5. So the mean is 260.8. If I subtract 65.5 from that, I'm going to get 195.3. That will be 1 standard deviation below the mean. And then subtract another 65.5 from the 195.3, I will get 129.8. That's 2 standard deviations below the mean. And then subtract another 65.5 from the 129.8, I will get 64.3. That would be 3 standard deviations below the mean. So now I got the adequate information that I need to answer problems A and B. So the answer to problem A is this. Well, here's the question. What is the approximate percentage of women with platelet counts within 3 standard deviations of the mean, or between 64.3 and 457.3? Well, if it's within 3 standard deviations of the mean, now we pretty much already talked about that. Within 3 standard deviations of the mean is about 99.7. So here, to answer part A, it's 99.7. Okay. And if you look at it, between 64.3 and 457.3, that's 3 standard deviations above and below the mean. That is 99.7%. Now, part B is this. What is the approximate percentage of women with platelet counts between 129.8 and 391.8? Okay, let's see here. 129.8 is right here. And 391.8 is right here. Notice that's 2 standard deviations below and 2 standard deviations above. And according to the empirical rule, within 2 standard deviations of the mean, we have about 95% of all the data values here. So we can say here, 95%. So that means approximately 95% of women will have platelet counts between 129.8 and 391.8. And that will be within 2 standard deviations of the mean. Okay. And finally, we'll look at Chebyshev's theorem. This is another concept helpful in understanding or interpreting the value of a standard deviation. Okay. Now, where the empirical rule applies only to data with a bell-shaped distribution, Chebyshev's theorem applies to any data set, regardless. It's not limited to the bell-shaped distribution. It could be any data set. Now, the unfortunate part is that the results are only approximate. Okay, so here's Chebyshev's theorem. The proportion or fraction of any data set lying within k standard deviations of the mean is always at least 1 minus k squared, where k is going to be any positive number greater than 1. So for k equal to 2 and k equal to 3, we get the following statements, which is this: at least 3/4 or 75% of all values lie within 2 standard deviations of the mean. And the other statement would be at least 8/9 or approximately 89% of all values lie within 3 standard deviations of the mean. Okay. So that's Chebyshev's theorem. Now let's apply that theorem to this example number 6. According to a random sample taken at 12 a.m., body temperatures of healthy adults have a bell-shaped distribution with a mean of 98.29 degrees Fahrenheit and a standard deviation of 0.57 degrees Fahrenheit. Using Chebyshev's theorem, what do we know about the percentage of healthy adults with body temperatures that are within 2 standard deviations of the mean? And what are the minimum and maximum possible body temperatures that are within 2 standard deviations of the mean? Okay, so to answer that question, we want the percentage of healthy adults with body temperatures that are within 2 standard deviations of the mean. So our K is going to be equal to 2. Now here we can use that formula of 1 minus 1 over K squared and just substitute K with the 2. So it'll be 1 minus 1 over K, which is 2, and that's squared. And 2 squared will be 4, so it'll be 1 minus 1/4. And we're going to type this in the calculator: 1 minus, and then left parentheses 1 divided by 4. And I'll come up with 0.75. But of course, as a percent, we move the decimal point 2 places to the right, so it'll be 75%. Okay, so in this case here, 75% of healthy adults have body temperatures that are within 2 standard deviations of the mean. Okay, and if you look right here, it's already given to you. Within 2 standard deviations of the mean, at least 3/4 or 75% of all the values here. So 75% of healthy adults with body temperatures that are within 2 standard deviations of the mean. And what are the minimum and maximum possible body temperatures that are within 2 standard deviations of the mean? We did talk about that using the range rule of thumb. The minimum was mu minus 2 times sigma. The maximum was mu plus 2 times sigma. If you recall, that was helpful in determining significantly high and significantly low values. So here the minimum is going to be mu minus 2 times sigma. In this case here, our mean, which is your mu, was 98.29 degrees. The standard deviation sigma was 0.57 degrees. Okay, so we're just going to substitute the minimum. We got 98.29, that's your mean, minus 2 times sigma, which is 0.57. So 98.29 minus 0.57 would be 97.72. Oh, I'm sorry, 98.29 minus 2 times, we got to do 2 times 0.57. That'd be 97.15. So that's the minimum. And then the maximum value that represents 2 standard deviations of the mean would be the same 98.29, which is your mean, plus 2 times 0.57. That would be 99.43. Okay, so in this case here, these are your maximum and minimum possible body temperatures that are within 2 standard deviations of the mean. Okay, the 97.15 and the 99.43 are the 2 values that represent body temperatures that are within 2 standard deviations of the mean. Okay. All right, so this should help you with the homework in section 3.2. Okay, and that will conclude this video on measures of variation. So please feel free to email me if you have any questions about the homework.